A fan uses electricity to rotate blades and push air outward. If we reverse the equation, we get a turbine. A turbine sits in an existing airflow, gets pushed by the wind, and extracts that kinetic energy to generate electricity. In this build, we will walk through how to convert a standard household ceiling fan motor into a functional micro wind turbine capable of charging a 12-volt battery bank. Our starting point is a standard 3-blade ceiling fan motor. These units are heavy, durable, and built to run smoothly. To turn this motor into a generator, we will need to integrate a few additional electronic components: high-power neodymium magnets, a bridge rectifier to handle the current, and a charge controller to safely manage the battery connection. Building a generator from scratch requires precise machining and tooling. By starting with a pre-assembled fan motor, we take advantage of its factory-engineered housing and smooth internal bearings, saving dozens of hours of fabrication. Step 1 is to remove the external casing screws and the capacitor. This exposes the internal motor assembly, which is where the actual conversion will take place. Here, we can clearly see the two primary components. The central stationary piece wound with copper wire is the stator. The outer metal ring that usually spins around it is the rotor. Take a close look at those concentric copper rings. These wires are extremely fine. You need to handle the stator carefully so you don't snap a connection or scrape off the insulating enamel. Next, pull the central copper stator away from the silver rotor ring. We are removing the original factory armature setup to make room for our new magnets. Before moving forward, wipe down all the internal surfaces of that outer rotor casing. It needs to be completely clean to ensure the adhesive for our magnets forms a secure, permanent bond. By separating and prepping these specific parts, we are setting up the hardware to reverse its behavior, shifting it from an induction motor that uses power to create motion into a generator that uses motion to create power. Standard ceiling fans use induction motors, which are manufactured without permanent magnets to keep costs low. To induce an electrical current when the fan spins, we have to add our own. Weak ceramic magnets won't work for this. We need to install high-power neodymium magnets to create a magnetic field strong enough to produce a usable voltage. These magnets must be glued to the inside of the outer rotor casing. They have to be spaced perfectly evenly to keep the fan balanced and the magnetic field consistent as it spins. This image illustrates the correct placement. The 4 dark rectangular magnets are positioned around the outer edge, carefully spaced so they will pass directly over the copper windings of the stator. When you reassemble the motor, slide the rotor back over the stator slowly. The neodymium magnets add extra thickness, and you must make absolutely sure they do not scrape against the delicate copper wires. Give the outer housing a spin by hand. It should rotate smoothly and freely. If you feel or hear any friction, open it back up and adjust the clearance. Once the clearance is right, reinsert the setter shaft and align the remaining internal components. This labeled diagram shows the exact sequence to secure the hardware back together safely. With the permanent magnets installed and the core reassembled, the mechanical build is complete. The fan can now physically convert the kinetic wind energy into an electromagnetic force. As the wind spins our new magnetic rotor, it induces an alternating current, or AC, inside the stator's copper coils. However, standard storage batteries require direct current, or DC, to charge. We wire the fan's output into a bridge rectifier, converting raw AC electricity into stable DC power. From there, wiring routes into a charge controller, and finally to our 12-volt battery bank. The controller acts as a safety gate. It monitors voltage and stops electricity flow when the battery reaches capacity, preventing damage. Since this entire setup will live outdoors, you need to apply a generous amount of high-quality silicone sealant to all wire exit points and casing seams to make the electrical housing completely weatherproof. Routing the electricity through this conversion and storage circuit ensures that the power you generate is actually reliable and ready to use when the wind dies down. Now we test the build. Mount the sealed turbine onto a sturdy pole, reattach the aerodynamic blades, and secure it in an area with clear, unobstructed wind flow. As the blades start spinning, we have to keep a principle of fluid dynamics in mind: Betz's law. This law dictates that no turbine can ever extract 100% of the kinetic energy from the wind. If a turbine captured all the incoming energy, the air would completely stop moving right behind the blades, blocking any fresh wind from getting in. Instead, as the turbine extracts energy, the exiting wind slows down and expands to a wider area, strictly limiting our maximum efficiency. To see exactly how much power our specific unit is capturing, we need to run a live multimeter test during a solid gust of wind. Hooking the leads up to our converted motor, the display registers a live voltage output as the rotor spins. The hardware is successfully generating electricity. Finally, check the status light on your charge controller. When it clicks on, it confirms that your newly harnessed wind energy is actively flowing into the battery bank. While a single motor provides a modest amount of power, connecting multiple units together can keep a battery bank charged for essential daily needs. Using hardware that is already widely available, this method creates a steady source of electricity for basic LED lighting and charging mobile devices.